Very well. I'll try and rather quickly look at the endogenous variable, single endogenous variable, instrumental variable estimator. What I'm switching to is a slightly different set of lecture notes, but I think it's got very similar, should have in fact the same notation. Can't quite guarantee that. We see how it works out. In fact, I'm discussing the case where we have u's on the right hand side rather than y's on the right hand side, and I have the following notation, which I think is slightly different, but you can soon see the resemblance, I think, in this note. Z2 are the set of instrumental variables, transformed instrumental variables, not in the first equation as before. Y2 is the second endogenous variable, the non-standardized endogenous variable. U is the error on the equation. Now what we have to do is to introduce an explanation for y, which I write simply y2 z1 p1 plus z2 p2 plus z3 p3 plus v. Of course, y2 is a vector, t by 1 vector. Z1 is the set of predetermined variables in the equation. Z2 the remaining instrumental variables as transformed. Z3 is any other predetermined variables in the model. P1 is then an appropriate dimension vector of reduced form coefficients. Maybe you'd expect me to be using pi's, but for some reason I've always used p's. Of course, what we then do is to multiply by z2 prime, etc. And because we have orthogonality between the z's, the only term that gives us something non-zero here is the z2 prime z2 p2 plus, and of course z2 prime v. Well, let me simply, the remaining two terms are zero, so let me simply write this z2 prime z2, which I can immediately replace by t times I, so I simply get t times p2 plus z2 prime v. Now, the simplest way of proceeding from here is to orthogonalize the u and the v. And what I do is to introduce u star, which is the residual on the regression of v on u. Alternatively, we can write delta equals sigma rho upon sigma v, where rho is the correlation between v and u, and sigma is the standard deviation of u, and sigma v is the standard deviation of v, and in fact it's convenient later to make that substitution. So this is just the usual formula for a regression coefficient. Then U star, of course, is going to be normally distributed, mean zero, variance, sigma squared into 1 minus rho squared. I'm sorry, U star being a vector, we need to put in the unit matrix of appropriate size. I've always been in favour of simplifying notation where one can, so rather than keep these expressions going, let me now introduce a few more vectors. First of all, I define little k, which is z2 prime v upon square root of t. Q is z2 prime u star upon square root of t. Then it's not too difficult to see that from the formula that I give for z2 primed y2, substituting that into the formula for b hat minus b, you have the following: p2 plus k upon square root of t, p2 plus k square root of t into square root of t b hat minus b is the same kind of thing at the other side. K upon square root of t into delta k plus q. Notice that really what I'm doing here is to explicitly take account of the mean of the z2 primed y2 variable, rather than work with non-central chi-squared. I'm really moving it around so that I can work with central chi-squareds. Now, the idea of this proof that's perhaps slightly unusual is the idea that we can define a variable which at first sight depends upon the k, but in fact when you sort it out has a distribution independent of k, so that one slightly simplifies the initial statement of the joint distributions that we're interested in. And what I do is to define a scalar vector q star, which is q primed into, well, let me write it down. The same multiplied by sigma u. If we look at the numerator, you know that q primed and k are independent of each other from the definition of u star. Therefore, if you consider the distribution of this variable q star rather you consider the distribution of the numerator conditional on 1k, the distribution is normal with this denominator as the standard deviation. So if you just divide by this variable, you get something which has got a normal distribution with zero mean and unit variance, and that distribution is obviously independent of k. So that means that the conditional distribution is in fact independent of k, which means that the unconditional distribution is the same as a conditional distribution. So that means that Q star is in fact, if you like, a T ratio. It's just distributed N01. That's the tricky bit of the proof. I mean, that's the only original idea in this derivation of the distribution. Well, now all we do is to write down the joint distribution of the various variables so defined. I actually find it convenient to define an appropriate chi-squared by rescaling all my variables so that they're variables which have simple 0, 1 normal distributions. So let me introduce psi, which is P2 prime k divided by sigma v P2 prime P2. So I've simply taken the P2 prime k, which obviously is going to turn up in the formulae that we're working with. Again, you see that really what I'm doing, I'm afraid, is simply avoiding working with a non-central chi-squared by introducing an appropriate way of defining such a non-central chi-squared in terms of a central chi-squared plus a normally distributed variable. And then if you consider my eta, which is k prime k upon sigma v squared minus this psi squared, you notice that what I'm doing is to take one variable psi, which is distributed n01 because of the rescaling that I've carried out here, and then that k prime k upon sigma squared is of course a chi-squared of degrees of freedom equal to the number of k's. The number of k's being m2, so k prime k upon sigma v squared is a chi-squared of degrees of freedom m2, and then I'm taking off a linear square of a normally distributed variable, which is a linear combination of the k's, rescaled so that it's in fact a chi-squared of degree 1. So the difference is going to be a chi-squared of degree m2 minus 1. In other words, I can write that eta is distributed a chi-squared degrees of freedom m2 minus 1. What's more, psi is independent of eta, and q star is independent of both of them, because we know it's conditionally only determined by q primed and k, and the same kind of argument about it having a conditional distribution, which is the same as its unconditional distribution, goes through here. And so we have independence of these three variables, and my estimator can be expressed in terms of these three variables. So what I'm going to be able to do is to express my estimator in terms of these three variables, all with simple distributions, and then to use the usual kind of transformation, integration, to get down to the distribution of b hat minus b. In fact, rather than play about with m2 minus 1, I'm going to introduce L equals m2 minus 1. Now, part of the reason for this is that L, if you like, is the degree of over-identification in this case, since we have that m2 is the excess of the number of instrumental variables over the number of predetermined variables in the equation. Then we have, if you like, an extra 1 for the endogenous variable, meaning that this is the difference between the number of instrumental variables and the number of estimated coefficients, which is the usual definition for degree of over-identification. Well, now, okay, let's, having explained what we're going to do, express everything in terms of these eta, psi, eta, and q star. Let's proceed to do it. Multiplied by psi. Well, if we sort out this, simply multiply up and then see what we have in terms of our previous variables, we find that we have two terms. The first obtained from the k, the second from the q. The first term is multiplied by delta throughout. And the second term comes from the q, and our definition is q star, and it turns out to be a rather exactly the same expression that we have over here. Well, perhaps I'd better write it down again, but let me just draw your attention to the fact that it is the same. To the half times sigma u times q star. Well, clearly that needs simplifying by introducing more notation. And so let's introduce first of all lambda squared, which is defined as T P2 find P2 upon sigma b squared. You notice that is something like a ratio of the variance of the systematic part of some endogenous variable to the corresponding random part. The only thing is that it's the amount of the variation of y2 that's explained by the z2 that occurs in the numerator, and as usual the sigma b squared in the denominator. Then we also define new variables, s, which is eta plus psi squared plus 2 lambda eta plus lambda squared. Now, that is simply what we have in the bracket here, rewritten. Actually rescaled by dividing by sigma b squared upon t, and then written in terms of lambda. So S is what we have up here, or related to it. I also introduce F. Again, rather a lot of arbitrary notation here. F is simply going to be a kind of standardized square root of t, p2 primed p2 divided by sigma u this time, multiplied by b hat minus b, again just to take some factors out of the expression that we're working with. And then I'm going to rewrite this equation as follows. Well, I suppose I'd better write that, if the camera can bear with that, over here so that I don't have to rub out the equation that I'm actually replacing. SF equals lambda s to the half times q star plus lambda delta sigma v over sigma rho, sigma u, sigma v. My fingers are anticipating what I was going to say, which in fact is that this ratio is in fact rho, the correlation coefficient, and then we have lambda psi plus psi squared plus eta, if you sort out what we have here. Well, now to move on from there, this is then equal to lambda s to the half q star as before, but then we find that if we substitute what s in here, we can write this in the form plus lambda rho, where rho is the correlation between sigma v and sigma u, sorry, between v and u, into s minus lambda into psi plus lambda, close second bracket. Now, what I'm interested in, of course, is to work out what the finite sample distribution of f is. We find that f is related to q star, psi and eta by this equation, and then what we want to do is to write down the joint densities of our variables, the three variables I've just mentioned, and then change the variable so that f is contained in the set of variables being discussed, and then to integrate out the remaining two variables. So let me write down the joint density of q star, psi and eta. Well, first of all, I'll write down the terms that correspond to eta being a chi-squared, being distributed as a chi-squared. Well, that gives us a half L plus 2 then on top here we have pi, and then gamma a half L, and then we have, yes, I'm sorry, I can't read my own notes. Those go in the bottom. So it's 1 upon all this lot, pi gamma a half L. Okay, so that's a constant term on the outside. Yes, part of this pi, the pi here actually comes from the two normal distributions. I've put together the whole joint density for the all the variables. So in effect, the two that we have here giving you a 2 pi comes from the fact that we have two normally distributed variables in the joint density. Then x minus a half into q squared plus chi squared plus eta. Take the 2 pi out of the bottom here and combine it with the q star squared and the eta squared. That gives you the two normal densities, and then in addition you have the chi squared distribution for the eta. I shall usually just be writing little p and then variables in a bracket to mean the joint density of that set of variables. And now let me make the first obvious transformation. That is that we want to now replace q star by f, and we can do that leaving eta and psi unchanged, so that our Jacobian just consists of the coefficient that we have here, which when we divide by s throughout is simply lambda times s to the minus a half. So in other words, we have d f dq star is lambda s to the minus a half. We have to multiply by that, in effect we have a dq star here, so we have to divide by this in order to get the joint density of f s psi eta. Well, so the outside term is going to become 1 upon 2 to the half L plus 2 pi gamma to the half L times lambda, since we're dividing by the. Then we're going to have an extra s to the half. Then we're going to have, as before, eta to the half L minus 1. Of course, it isn't a half multiplied by L minus 1, it's a half L minus 1. Then we're going to get the same exponential, but now what we have to do is to substitute what q star is in terms of f into our equation, and I'll write down the result of doing that. Rather complicated exponential, and we get the following terms. Close large bracket, all squared, plus psi squared plus eta. Let me just check that I have everything where it should be. Yes, that's okay. No, it isn't quite. Yes, I need another bracket. Yes, that's right. Another bracket there, another bracket there, and then close the large bracket.
Where does the square bracket go?
The square bracket goes from here to here. That's all squared.
No, sorry, I didn't mean that there's a square bracket inside the yes as well.
Oh, yes, I'm sorry. Yes, f upon lambda minus rho, yes. That's the wrong one. That should have been the square bracket now. So this is f upon lambda minus rho. Well, now what we have to do is to eliminate the psi and the eta just by integrating this with respect to psi and eta. In order to do that, we need to transform our variables. And the transformation I'm going to employ is, first of all, to change from eta to s using the equation defining s that I wrote up already, and then to change the eta variable as I'll indicate. Let me first of all change eta to s, what you notice there is that s is eta plus xi squared plus 2 lambda xi plus lambda squared, so that the Jacobian of that transformation is simply 1. We're just making a single transformation, and the Jacobian is the ds by the eta, which is 1. So there's no change in the form here. Then what I'm going to do is to also introduce a second transformation immediately after that. Mu equals xi plus lambda over s to the half. Now you notice that in fact that gives you that eta is equal to s into 1 minus mu squared, so it's convenient to make that substitution for eta in this form immediately. You notice that this in effect is mu squared times s. Take it to the other side and you get eta equals s into 1 minus mu squared. The Jacobian of this transformation from mu to eta is given by d mu by d eta equals s to the minus half. So this in fact is the only Jacobian required here. I've said d mu by the eta, I meant of course d mu by d psi. Or in other words, shall we write it in the form which I have in the paper, I think it makes it easier to see what's involved, is s to the half d mu. And that is going to give us then another s to the half, which multiplied by that s to the half just gives us a total s there. We also are replacing eta by s into 1 minus mu squared, so that this eta squared will give us s to the L minus 2. So that, in fact, finally writing down all the expressions that I have there, you find that you get the following. That the joint distribution of fs mu is equal to and that is unchanged in effect from what we had before. Then the s turns up with the power half L, the 1 minus mu squared to the power half L minus 1, and then an exponential usual, no, wrong place. Yes, that's right, plus s to the half mu lambda minus, again, f over lambda minus rho, always turning up this thing, we want a 1 there and another bracket there. It's lambda into 1 minus yes, I'm sorry, 1 minus rho into f over lambda minus rho. So that's the coefficient of s to the half mu. And then finally, minus a half lambda squared rho squared mu squared minus a half lambda squared. So there's an extra half on the lambda squared. Yes, I'm finding it difficult to keep track of all these brackets that I have here. I'm not right. That closes there, minus half lambda squared. This final bracket corresponds to the bracket here. Now, this doesn't look at all a nice expression to integrate with respect to the mu and the s. Notice that one restriction we have is that 1 minus mu squared is eta upon s, but that if you look back to eta being distributed as chi-squared means that eta is always positive, that the range of eta that we're interested in is always positive. Likewise, s is always positive, and clearly from its definition eta is always less than s, so that this 1 minus mu squared is always between 0 and 1, and that means that mu has the property that its absolute value is less than 1, in other words, that it lies between plus 1 minus 1. Clearly, what we have is a repetition of similar coefficients here, and it's convenient again, I'm afraid, to introduce even more notation and define f is f upon lambda minus rho squared, and g is lambda into f minus rho into rho is in fact then equal to lambda into sigma squared minus all divided by sigma u squared. What is sigma squared? Sigma squared is actually equal to, yes, I've been a little remiss. I haven't in fact defined sigma u squared yet. Sigma u squared is the variance of the q star and is equal to sigma squared. I previously used sigma squared to mean the variance of u. So sigma u squared throughout here has been the variance of u star, or I should say q star. U star, if you remember, was defined as u minus delta v in other words, it's the residual of this regression of u on v. And sigma u squared is defined as the variance of u star. And so here, in this formula, if you look back, you will find that if you combine together the lambda, yes, I'm sorry, I've actually missed out at lambda here. If you can, yes, I ought to write this in the form what I have here, lambda minus f minus lambda delta sigma v upon sigma u multiplied by delta sigma v sigma u. You can combine together the two terms in lambda here to give you lambda into 1 plus delta squared sigma v squared upon sigma u squared. And that gives you your sigma squared back again, and you can write this then in the form lambda sigma squared minus delta f sigma v sigma u all divided by sigma u squared. Finally, we introduce h, which is lambda squared delta squared sigma v squared upon sigma u squared. Wherever I had a row here, you can substitute delta sigma v sigma u. And you find then that we have the exponentials can be written. So let me just write again this exponential down again. Take that in a great bracket, write it down again in the form that it's exponential first of all f minus a half fs, then plus, and this term is just plus s to the half mu g, capital G, and then finally plus, minus a half h mu squared. So we have, in effect, one term that's quadratic, if you like, in s to the half, another term which is a product of s to the half by mu, and a final term which is quadratic in mu squared. And we want to integrate up with respect to mu and s, with mu confined to the range -1 to +1. Now, yes, you're right. There's also e to the minus a half lambda squared, which is going into the constant term, so it isn't going to worry us very much. Now, at this stage, what happens, which makes it possible to get an expression, but of course a rather difficult expression to interpret, is that we simply expand the last two terms in the usual power series for the exponential, and then integrate term by term. Of course, we have to justify this, but they're both, the exponential, of course, has the advantage of being a convergent power series for all values of the variable, and uniformly convergent for all finite s, and certainly for all mu bounded between 1 and -1. So it is in fact permissible to make these expansions and integrate term by term. And so I replace the exponentials by the corresponding power series. So it's convenient certainly for me to do the usual replacement by rubbing out, which means that I take the exponential minus a half lambda squared to the constant term on the outside. I keep the exponential minus a half fs, and I expand the other two, r equals 0 to infinity, s equals 0 to infinity. Then we're going to get gs to the half times mu to the power r over factorial r, and then also minus a half h mu squared to the s over factorial s. In fact, half these terms are going to disappear because when you have a term here which gives you an odd power of mu, and then you multiply that by 1 minus mu squared to the half L minus 1 on the outside, you still have an odd function of mu, which when you integrate it from over -1 to +1 gives you 0. So you can forget about half these terms. The even powers of mu, of course, give you the following, that 1 minus 1 mu to the 2j, for example, 1 minus mu squared to the half L minus 1 d mu gives you a beta function when you transform from mu to, say, z equals mu squared, and that in fact gives you gamma j plus a half, gamma a half L, gamma j plus a half L. You notice that there's going to be a cancellation. The gamma to the half L here is going to cancel with the gamma to the half L that we've got here. So, okay, let's do that first. Let's integrate with respect to mu using this formula. What are we going to get? We're going to get PFS, direct distribution of F and S. Well, e to the minus a half lambda squared as before, cancellation of the gamma to the half L, and so we're left with lambda 2 to the half L plus 2, and that's all we have for the outside term, and then s to the half L, exp minus a half s, fs, sigma sigma as before, but now the sigma with respect to r runs only over the odd, the even values of r. So let's write R equals to 2k, and then sum over k. And you find, gathering it together, of course, g s to the half to the power r is just g to the 2k s to the k minus a half h to the s, little s, factorial 2k factorial s, and then ratio of two gamma functions. Well, actually, in order to make room for all that, so I've got myself a little into the corner, let's take the sigma a little bit forward, and then put gamma to the k plus s plus a half over gamma to the k plus s plus a half plus a half L. That is when you've sorted out what the coefficient is here. It's mu to the 2k from here and mu to the 2s from here. So it's mu to the 2k plus s. And if you look at this formula here, you find that that means that j is equal to k plus s in this formula here, from the fact that we've got a mu to the 2j up there. Well, that's what we've got. That's our formula. Now, what we have to do is to integrate with respect to s. And of course, integrating with respect to s, what we've got here, if you like, is a standard chi-squared distribution, sums of standard chi-squared distribution integrals. S to the L plus K is the typical value for the exponent, half L plus K is the typical value of the exponent of S, multiplied by x minus a half Fs. We can integrate that fairly easily as a modified gamma type distribution. And so we are going to carry through that integration. But before we do that, we can see that we can extract the coefficient of s to the k plus a half L. Simply take the s to the k plus a half L outside here and already take out a single integration, a single summation with respect to s in defining that coefficient of s to the k plus a half L. All we have to do, in fact, is to define the hypergeometric function of the confluent type. It's actually defined as follows. The confluent hypergeometric function f11 is usually denoted by, because in fact there are more complicated hypergeometric functions which have got different orders of suffix here, but this is a standard type of confluent hypergeometric function. A power series in x depending upon the two parameters a and b, defined 1 plus a, b, like 1 times x plus a plus 1, b plus 1, 2 x squared. The general term is fairly clear, and one way of writing it down is to write it in the form gamma b gamma a summed up on I gamma a plus I gamma b plus I x to the power I upon factorial I. Of course, then what you're doing is to use the property of the gamma function. The gamma, say, c plus 1 is equal to c times gamma c. And if you repeatedly substitute that formula here and then cancel out with the gamma b and the gamma a that you have on the outside, you find that you get again this formula for the hypergeometric function. This features in the textbooks of analysis as the solution of one kind of class of second order differential equations, but we don't need to go into that here. But essentially what you see is that you can discuss this in terms of its ordinary power series properties to find that it only converges if x is in the interval +1 to -1. And that's the end of the tape. Yes. Over identification in the usual way, but I've, in talking about instrumental variables, often find it convenient to talk about the difference between the number of instrumental variables and the number of unknown coefficients as the degree of over-identification. Continue with this proof. Now, if you sort out what you have here, you see, you find that if you now take the summation with respect to S for a given K, the result of the summation doesn't depend upon S in the sense that you can take the S to the K outside. Let me do it immediately. Write this in the form. And now sum with respect to S and find that you have something which doesn't depend upon S, and therefore from the point of view of the stochastic variables can be regarded as just a constant. And if you now make use of this definition of the f function, the confluent hypergeometric function, you find, again writing the whole thing down again, well, the same constant as before, so let me not bother with that. Yes. Sigma well, actually it will be more convenient to keep the s to the half L exp minus a half fs together for the time being, and then have the single summation with respect to k. multiplied by the F11 k plus a half k plus a half L so those are my two parameters A and B that I referred to in my definition of the F11. And then this all is multiplied by minus a half h. Sorry, not multiplied by half h. The minus a half h is the variable occurring as the x in my definition of the confluent hypergeometric function. In other words, we're going to find that we've got a power series in minus a half h here. Now, from my previous discussion, it emerged that we could think of this as being a double integral with respect to s and mu, and that because of the properties of the exponential function, this could be regarded as being a uniformly convergent, the double integral of a uniformly convergent series. It follows that at this stage it is permissible to integrate with respect to s and take the series term by term. And so we can do this immediately using the formula. Well, let me write it down again separately. Infinity 0 x minus a half fs s to the half j ds is equal minus a half f, so a half f to the minus a half j plus 1 gamma k plus a half 2 to the 2k all divided by pi to the half. Notice that we've got a factorial 2k in the bottom here, so we can also make use of the well-known formula for what are called duplication formula for gamma functions, that a factorial 2k is the same as the gamma 2k plus 1 function, and that is equal to factorial k gamma k plus a half multiplied by 2 to the 2k I'm sorry, I've done a rather foolish thing. I've taken one line from one formula and put it on the end of another. There what I wanted was simply gamma to the half j plus 1. But now what I want here is what I had before, 2 to the 2k divided by pi to the half. So let us simultaneously do this integration and at the same time replace the 2k by this formula for the 2k. We find that that in fact gives us a simplifying cancellation. And we end up with a formula for the density of the F, which I will now proceed to write down, again by making space. I have to take this out and simply say that the probability density of F is the following. Multiplied by the f11 function that we had before, k plus a half, k plus a half L plus a half minus a half h. Which is, of course, not a very illuminating formula, but it's what we must now try and interpret. The way, of course, that we have to interpret it is by now seeing what the various capital F, capital G, capital H variables that we have here, how they're related to our original b hat minus b. What you notice, of course, is that even to get to compute this density function, you have to have, first of all, a subroutine which will compute the confluent hypergeometric function, and that in itself involves either having one of these special computer approximation programs, or more likely, because these things are usually not available, actually summing the infinite series up to a sufficient number of terms to get an adequate approximation here. Then you have to do this for an infinite number of k's in theory. Well, again, that means for a large enough number of k's that the second infinite series converges. So it's not an easy matter, in fact, to compute this numerically. And as we shall see, except upon the tails of the distribution for large values of b hat, beta hat minus b, the g squared upon 2f, which, if you like, is the variable that's occurring in this power series, is not going to be very different from 1. It's going to be this is going to be small on the tails of the distribution, this ratio, and so this is really best adapted for computing the values of the density on the tails of the distribution rather than in the center of the distribution. Let us see how that works out. First of all, look at the definition of f. Sigma u squared f is sigma u squared, etc. Well, sigma u squared plus delta squared sigma v squared is, by definition, still, since sigma u squared is the variance of the residual of the regression of u on v, the same as sigma squared, where sigma squared is the variance of u squared, the original u squared. Then from the definition of delta, we see that this can be written in the form, could there be a 2 missing at that stage? Yes, indeed, there should have been a 2 in here. And delta times sigma v is rho times sigma. So this is rho sigma u plus sigma u squared b hat minus b all squared. And so it's a simple kind of quadratic form in b hat minus b. Sorry, not quadratic form, quadratic in b hat minus b. If you work out f in the same way, you find that g squared upon 2f is equal lambda squared sigma minus rho sigma u b hat minus b close first bracket all squared divided by, and the 2f, we have f here already, so we find that that's equivalent to 2 sigma u squared sigma squared minus 2 b hat minus b, etc. Sigma u rho plus sigma u squared b hat minus b all squared close outside bracket. If you look back at h, by the way, I ought to have made this point before, h does not depend upon b hat minus b, it just depends upon the original variances. So the only terms that in this expression that depend upon b hat minus b is the ratio here, which I've already written down, and the f which occurs out here. You also notice that this has the tendency, as b hat minus b becomes large, to tend to a finite limit, because it's the ratio of 2 quadratics. And that limit is in fact given by lambda squared sigma squared upon 2 sigma u to the 4. So the final effect of that is that when b hat minus b is sufficiently large, then this whole expression is converging to the limit value, which is obtained by taking the limit value lambda g squared upon 2f and substituting it in the power series. And so in effect at that stage, the density is varying with b hat minus b according to the minus a half L plus 1th power of f. And you see that that is behaving like an inverse power, because again, only the last term here is relatively large, that term is relatively large compared with the earlier terms. In fact, the density is behaving like let me see, sigma u squared b hat minus b squared to the minus a half L plus 1. Or in other words, like is proportional to b hat minus b modulus 3 minus L plus 2. So upon the tails we have this kind of straightforward inverse power, negative power behavior of the density. And I suppose the main thing that enables you to see is what moments of b hat minus b exist, are finite. In fact, from this you see that the L power is well defined, that b hat minus b to the L integral p b hat d b hat is behaving on the tails. Its convergence is determined by that it behaves like b hat minus b squared is proportional to b hat minus b squared db hat on the tails. Of course, if you move up to the L plus 1th moment, you find that it's behaving like 1 upon b hat minus b to the minus 1, and so the moment would not be defined. So this is really the chief conclusion that can be easily drawn from this form of the density, that the moment of order equal to the degree of over-identification is finite, and no other moment, no higher moment is finite. Of course, from this people have computed the exact density and integrated that up numerically to get the exact cumulative distribution function. But what is not easily available, for example, is any way of seeing what happens as t goes to infinity. And in particular, it's not easy from this to derive the asymptotic distribution. I'll say some more about that next time. We're clearly running to the end of our time. Well, any immediate questions?